One of the most commonly asked questions at data science interviews is about overfitting. A recruiter will probably bring up the topic and will ask you, what's overfitting and how do we deal with it? Fortunately, in this lesson, we'll address this issue and you won't be surprised when it comes up. There are two concepts that are interrelated, underfitting and overfitting. They go together. Understanding one helps us understand the other and vice versa. Okay. Broadly speaking, overfitting means our training has focused on the particular training set so much it has missed the point. Underfitting, on the other hand, means the model has not captured the underlying logic of the data. It doesn't know what to do and therefore provides an answer that is far from correct. Let's explain this with graphs, as it is much more intuitive and cooler. First, we will look at a regression, and then we'll consider a classification problem. Here, we can see several data points following the blue function with some minor noise. A good algorithm would result in a model that looks like this. It is not perfect, but it is very close to the actual relationship. Okay. We can certainly say a linear model would be an underfitting model. It provides an answer, but does not capture the underlying logic of the data. It doesn't have strong predictive power. It's kind of lame. Underfitted models are clumsy. They have high costs in terms of high loss functions, and their accuracy is low. You quickly realize that either there are no relationships to be found, or you need a more complex model. Alright, let's check an overfitted model. Here it is. Now that you see this picture, we can say overfitting refers to models that are so super good at modeling the training data that they fit or come very near each observation. The problem is that the random noise is captured inside an overfitted model. Let me elaborate on this a little further with an example. Imagine you are trying to predict the euro-dollar exchange rate based on 50 common indicators. You train your model and get low costs and high accuracies. In fact, you believe, with 99.99% accuracy, you can predict the exchange rate. Confident with your machine learning skills, you start trading with real money. Unfortunately, most orders you place fail miserably. In the end, you lose all your money because you trusted the amazing model so much. What happened with your model is it probably overfit the data. It was trained to explain the training data so well that it missed the point. Instead of finding the dependency between the euro and the dollar, you modeled the noise. The noise in this case consists of the random decisions of the investors participating in the market at that time. So, shouldn't the computer be smarter than that, you may ask? Well, we explained the training data well, so our outputs were close to the targets. The loss function was low, and the learning process worked like a charm in mathematical terms. However, once we go out of the training set and meet the real-life situation, we see our model is actually quite bad. First rule of programming states that the computer is never wrong. It is us who made a mistake. We must keep issues as overfitting in mind and take care of them with the appropriate remedies. As a whole, overfitting can be quite tricky. After seeing this beautiful graph, you probably believe you can spot an overfitting problem. But remember that, in the Forex example, there were 50 indicators, which means we need a 51-dimensional graph, and I don't know about you, but my senses work in 3 dimensions only. But first, we will look at a classification example. Here's our example. There are 2 categories. One of them is cats, and the other one is dogs. A good model explaining all the data looks like this. A quadratic function with a few errors. Following the logic we saw in our previous example, what would be an underfitted model? Well, of course, a linear model. Linear models are not very smart. Often, a simple linear model underfits if the data is not transformed. Around 60% of the observations would be classified correctly with an underfitted model. Now, an overfitted model would classify the observations perfectly, right? It has correctly identified all the cat and dog photos in the dataset. But once we give it a different dataset following the same quadratic function logic, it will perform poorly. Alright, let's conclude lesson with the following remark. What is a well-trained model then? Well, it is somewhere between an underfitting and an overfitting model. This fine balance is often called the bias-variance trade-off. Oh, and if you are a meme fan, there's this Facebook page, Machine Learning Memes for Convolutional Teens, that I follow. Some time ago, they posted a photo of a bed that beautifully exemplifies overfitting. It fits some people perfectly, but on average, missed the point of being a bed. Memes are an interesting way to check knowledge. If you find it funny, you most probably understand the concept.